Today I'm giving you help on how to do net force equals mv squared over r problems, and it will help if you have this sheet, but if you don't have it, you can simply copy down the problems as I post them, and maybe you have to pause the video as you watch. In the first example, I'm going to do just a string hanging down with a 4 kilogram mass. And the question is, what's the tension in the string? By the way, the length of the string is 0.5 meters, as in the next example too. In this case, it's just hanging down, doing nothing, it's just a hanging mass. And so the force of gravity, 40 newtons down, perfectly balances out the tension up, allowing it to have equilibrium, no acceleration. So here, the tension is simply 40 newtons. In the next case, it's not in equilibrium. It's swinging in a circle. And to go in a circle, it has to accelerate. Therefore, it's going to need an extra outside force. The force of gravity is still 40 newtons down, but it swings upward. It swings centripetally in a circle. In that case, we could say that the net force causes circular motion, and by circular motion I say mv squared over r. That's net force equals ma, where a is v squared over r. Here, the net force is 40 newtons and tension, but the tension is the larger of the two because it accelerates up. The tension wins. So this will become tension minus 40 down is mv squared over r. The mass is 4 times the velocity squared, that's 6 squared. In this case it's swinging at 6 meters per second, divided by the radius, which is 0.5. A little calculation, and we see the tension is 328 newtons. Much larger than the original tension of only 40 newtons, and it's much larger because it's a very small radius swinging pretty fast, and it's a heavy mass, so that accounts for all of that. Next example. In this example, we have a 70 kilogram passenger in a cart traveling along a curve of radius 60 meters, like maybe the bottom of an amusement park roller coaster, and it's traveling at 30 meters per second. And the question is, find the normal force at the bottom. The normal force at the bottom is going to tell you how you would feel in the cart. Now you've probably been on a swing and noticed that you feel extra heavy at the bottom. You feel extra heavy because the normal force is lifting you up, pushing you up to go into the circle. Watch this. As the cart moves forward, it continues. An object in motion remains in motion in a straight line at constant speed. But that of course doesn't happen because there is a track right there. So as the cart goes forward, it hits the track, which deflects it up. As the cart goes forward, it hits the track, which deflects it up. All the time the track is pushing it upward with a force, the normal force, which is probably bigger than the weight. Otherwise, if the weight, 700 newtons, was larger than the normal force, up, the normal force up n, if the weight was bigger, then it would go down. But it doesn't go down, it goes up. So the normal force must exceed the weight. Start with net force equals mv squared over r, because it moves in a circle of radius r. Plug in the two forces, n up and weight down. Normal force minus the weight equals mv squared over r. Let's plug in some values. 70 times v squared, that's 30 squared, over r 60 meters. And we'll get the normal force is 700 plus whatever this is. And a quick calculation gives you 1750 newtons. Now, you might wonder, what would that feel like? Well, they often talk about it in terms of the number of G's, or the G-force you would feel. 1 G would just be 700 newtons, your normal weight, the normal force. But in this case, it's 1750 over the normal amount. And that comes out to be 2.5. So it's 2.5 the normal amount of gravity, or 2.5 G's. That's what it would feel like. You would feel 2.5 times as heavy. Let's do another example. In this example, we have a cart on top of a hill moving at 6 meters per second, and it's going over a curve of radius 23 meters, and at this moment over here it's at an angle of 30 degrees. The change in height is marked right here, and the goal is to find the normal force at the top and find the normal force at 30 degrees. Let's start by making a statement. On a hill, in average circumstances, you would expect the normal force to be mg cos theta on a hill, based on theta, the angle of the hill. But is this theta the same angle of the angle of incline? I'm going to argue that it is. Because right here, at 30 degrees of incline, and if you trace it back, here it's at 0 degrees of incline, 1, 2, 3, 4, 5, 6, 30 degrees, but 90 degrees of incline. So you can see that this must be at 30 degrees of incline as well. You can do a geometry argument, but I wouldn't waste the time at the moment. Take a look up here. We have the force of gravity pulling straight down, mg. It weighs 4 kilograms, so it's 40 newtons of gravity. And that also happens over here. But let's focus on this one first. Up here we have also the normal force pushing it up, and we wonder which one's bigger. Well, the cart doesn't go up, and it doesn't go in a straight line, which if they were equal, it would go in a straight line. mg, 40 newtons, must be bigger than the normal force because it goes down the hill. Let's figure out what the normal force is. In the first case, we have net force equals circular motion. The object is moving in a circle. It's confined to move along this surface. We have gravity winning the tug of war. 40 newtons wins over the normal force, which we don't know how big it is. But we do know that it's accelerating down, or toward the center of the circle. So we'll say m4 times v squared, 6 squared, over r, 23. So now we got it. 40 minus that is the normal force. 6. So the normal force is just 33.7 newtons. A little bit less than 40 at that moment. What about this moment? Here we have gravity still pulling straight down, 40 newtons. Nobody is denying that. There is a component of gravity down the hill, mg sine theta, which you could figure out. I think it's 20 newtons, because the force of gravity downhill is the sine of theta. This is definitely theta, because alternate interior angles are congruent. So, and the sine of 30 is a half, and half of 40 is 20. But that 20 is not relevant at the moment. It causes it to accelerate down the hill, which is why it's gone from 6 to 10. In this direction, though, we have mg cos theta. Mg cos theta, which is causing it to accelerate toward the center. Mg cos theta is very relevant. The normal force pushes in this direction, causing it to not accelerate toward the center. Let's figure out what the normal force is. Net force equals mv squared over r. We have mg cos theta pulling it toward the center, mg cos theta, which must win the tug of war because mg cos theta actually causes it to go toward the center in a circle, like any centripetal force, but n is away from the center, a center fleeing force. The winner has to be centripetal because it actually moves in a circle. Mg cos theta less the normal force causes centripetal motion. 4 times 10 squared for the velocity divided by 23 radius. plug in for mg cos theta and get 34.6 minus some number is that? Is 17.4. So with a little math, the normal force works out to be 17.2 newtons, which is less than 40 newtons, of course, and also less than mg cos theta. It's beginning to fall off the hill. Have you ever been on a roller coaster that went over a hill? You feel like your stomach is floating in the air as you fall over the hill, and this is the reason. The track is abandoning you. Like maybe you drive over a steep hill in a car. Don't do this too quickly. But the car will abandon the floor and you will be floating in free fall temporarily. It's not good for your intestines, you see. They tend to expand into the space that your stomach was usually squeezing them into, making you feel woozy. When do you think it falls off? You can predict the moment when it falls off by taking the limit as the normal force goes to 0. Or you could just say set normal force to equal to 0, and that will help you figure out what angle or what velocity something will fall off a curving track. In our last example, consider a cart at an amusement park making a loop-the-loop, and it has a mass m of a radius r, and the velocity at the top is called v1, the velocity at the bottom is called v2. Now I want to be clear, despite the name, v2 happens first as it's on its way up, and goes up there to the top position where the track is going to push on the cart with a normal force called N1. At the bottom the normal force is called N2. The steps are find the normal force at the top and then prove that normal force 2 is greater than normal force 1. For part A, net force equals mv squared over r. Have you gotten the message yet? Whenever something's moving in a circle, this is true. The net force at the top is, well, let's take a look. We have mg down, and the track pushes on it down. We have two forces working together to push it down. mg pulls, but whatever word you want. mg plus normal force working together equals mv1 squared over capital R, the radius. What are we trying to find? The normal force at the top. So the normal force at the top needs to be mv1 squared over r, but gravity helps, so it doesn't have to work so hard. The smaller the velocity, the smaller the normal force has to be, which means when you go on a loop-the-loop, you better have enough velocity or else there won't be a normal force to push you and you're going to feel like you're falling, and that's very uncomfortable. Part B. Show that the second normal force is greater than the first. Well, the second normal force happens down here, and down here gravity is of course still straight down, mg. But if it's going to go in a circle, then the normal force has to be up. N. Alright. Who wins? Well, the normal force has to push harder than mg, so the normal force must exceed mg. So, for part B, normal force is up and wins, minus mg, which is down, and is equal to ma, v squared over r. This is v2, and this is capital R over r plus mg. Is that bigger than this one? Well, you bet it is. Especially when you consider that as it goes up the hill, it might